Graphing and linear equations with two variables. We've already reviewed linear equations with one variable. We recognize an equation because it has an equal sign. If all the variables have an exponent of 1, it's a linear equation. But now we're going to add a second variable, not just an x but also a y. For instance, the equation 2x plus y is equal to 8. A linear equation with two variables, each solution will be an ordered pair. It has to have a value for x and y. For instance, the point 4, 0. When x is equal to 4 and y is equal to 0, the left-hand side equals the right-hand side in the equation. 2 times 4 is 8, plus 0 is equal to 8. Another solution to this equation, the point 3, 2, the point 2, 4. They can certainly be negative values. For instance, the point negative 1, 10. 2 times negative 1 is negative 2, plus 10 is still equal to 8. And decimals and fractions as well. 2 times 1/2 is 1, plus 7 is equal to 8. So we could keep going and going, identify solutions to an equation. So there's infinitely many solutions. We can't list them all out on our paper. So what we do is we graph the equation. It's going to graph a line, hence a linear equation. A line is made up of infinitely many points. Every point on the line will be a solution to the equation. Likewise, every solution to the equation will be a point on the line. So one method to graph a line is to just begin plotting points. For instance, the point 4, 0, the point 3, 2, the point 1/2, 7, and so forth. All the points should fall in a straight line, hence sketching the line of that equation. But the easiest and the quickest way to graph an equation is using the form slope-intercept form. Pretty much when an equation, linear equation, is not in slope-intercept form, the first thing we want to do is get it in the slope-intercept form, which is y is equal to mx plus b, where m represents the slope of the equation. In other words, basically measures the steepness of the line. And b tells you where the y-intercept of the equation will be. The y-intercept will always be at the point 0b. Likewise, a y-intercept is just given by the equation, but most lines will also have an x-intercept, where the line touches or crosses the x-axis. The x-intercept is at the point x0. You plug in a 0 for y. So any linear equation will basically fall into one of four types of lines, or one of four categories of a graph. A line will either increase, decrease, be a horizontal line, or a vertical line. Increasing and decreasing lines will both have an x and a y in the equation. Horizontal lines only have the variable y, and vertical lines only have the variable x. So it's real easy to identify horizontal and vertical lines as long as you know what you're looking for. Look at those variables. The slope of the line also ties into what type of graph it is. If the slope is positive, the line is going to increase. If the slope is negative, it's going to decrease. If the slope is equal to 0, it's going to be a horizontal line. And if there is no slope, or if the slope is undefined, it's a vertical line. So let's graph another equation. Linear equation 4x plus 2y is equal to 10. As I just said, the first thing we want to do for an equation that's not in slope-intercept form is get it in the slope-intercept form. So a little bit of algebra, solve for y. Begin by subtracting 4x from both sides. And divide everything by 2, so y is equal to negative 2x plus 5. Now we did not change the value of this equation. These two equations are the exact same. They just look different in different forms. So now that it's in slope-intercept form, we know a lot more about that line. We know that the y-intercept is at the point 0,5. We know the slope is negative 2, so it's going to be decreasing. So all we have to do is find another point that the line passes through, which the slope will help us do that using the saying rise over run. If the slope is negative 2, we can change into a fraction by putting a 1 under it. The numerator is the rise, tells us whether we go up or down. So negative 2 means we go down 2 units. The denominator is the run, tells us whether we go left or to the right. So a positive 1 tells us we go to the right. So we have 2 points that the line passes through. All we do is sketch them, giving us the graph of the line. A line with y-intercept 5 and a negative slope, so it's decreasing. Example 2, another linear equation. We recognize that it only has the variable x, which means it's going to be a vertical line. So we begin by solving x. X is equal to 3, so it's simply a vertical line through 3. Now we need to review functions. The definition of a function is an equation such that for each input, there's exactly one output. So let's look at a basic linear equation to illustrate that. Y is equal to 2x plus 1. We know that there's infinitely many solutions, so we can begin finding some, construct a t-table, randomly choose some values for x, plug them in order to solve for y. For instance, when x is equal to 0, y is equal to 1. When x is equal to 1, x is equal to 3. When x is equal to negative 2, y is equal to negative 3, and we can keep going. But what we see here is that for each input, for each value of x we plug into this equation, we get exactly one value for y back out. So this fits the definition of a function. For each input, there's exactly one output. So it is a function. So we can write it as a function using the notation f of x is equal to 2x plus 1. The letter out in front is just the name of the function. Typically we use f, but it can be any letter, followed by a set of parentheses, and your value for x, or your input, is found inside. So the function f of x is equal to 2x plus 1. And that notation f of x simply replaces y. It has all the same properties, so you could even rewrite it back as an equation y is equal to 2x plus 1. We evaluate a function if I ask you to find f of 1. Whatever's inside the set of parentheses is your input. So that's what you would substitute in for x, allowing you to solve for y, which of course is 3, exactly the way we found our point 1, 3. So the math doesn't change for a function. The only thing that really changes is the appearance, the notation, the way it looks. For each function, there will be a domain and range. The domain is a set of all possible values of x. In other words, everything you can substitute into a function. The range is a set of all possible values for y, everything you can get back out of a function. So let's apply that to absolute values. We've been working with absolute values. The most basic absolute value equation there is y is equal to absolute value of x. If we have no idea what the graph of this equation looks like, we could construct a t-table, begin substituting values for x in order to solve for y. For instance, 1.002233, negative 1, positive 1, negative 3, positive 3, and begin plotting the points, we should get a pretty good idea what that graph looks like. So the graph of an absolute value is always going to be in the shape of a V. This particular equation, y is equal to the absolute value of x, is in the shape of a V that opens up, where the point called the vertex, where the direction changes, is at the origin. And since we noticed that for each input there is exactly one output, it is a function, so we could write it as a function. F of x is equal to absolute value of x. Since it's a function, it has a domain and range. The domain set of all possible values for x, so we look at the x-axis. Every single point on the x-axis will lie somewhere on that graph. Even if you go way out here to the left, if you go up high enough, it'll touch the graph. So the domain is going to be all real numbers, or negative infinity to positive infinity. The range, set of all possible values for y, we need to look at the y-axis. Now every number on the y-axis will not lie on that graph. All positive numbers will, but not any negative numbers. The lowest value, or the smallest value for y, for this function is 0. So the range would be all the values for y from 0 to positive infinity, including 0. So we have a bracket next to it. So if you look at example 1, graph the function f of x is equal to the absolute value of x minus 4. So absolute value function, still going to be in the shape of this V, but that negative 4 is going to move it somewhere around the graph, either up, down, to the left, or to the right. If we can find the vertex, we'll know exactly how it affects the graph. So the vertex, once again, nothing more than a point in ordered pair. find the x-coordinate, which is real easy to do. You just take what is inside the absolute values, set it equal to 0 and solve. So in this case, x minus 4 is inside the absolute values, set that equal to 0 and solve, which gives us x is equal to positive 4. So the x-coordinate of the vertex is 4. To find the y-coordinate, just plug that into the function. Absolute value of 4 minus 4 is, of course, just 0. So the vertex was at the origin. It moved over to the point. It moved over to the point 4, 0. The shape of the graph is still exactly the same, still in the shape of a V. It still has a domain and range. The domain, every value on the x-axis still lies on the graph, so the domain is still negative infinity to positive infinity. The range, the lowest point on the y-axis, is still 0, so the range 0 to positive infinity. Example 2, f of x is equal to absolute value of x plus 3 minus 1. So once again, we want to begin by finding the vertex. Take whatever is inside the absolute value, the x plus 3, set it equal to 0 and solve, which gives us x is equal to negative 3. So the x-coordinate of the vertex, negative 3. To find the y-coordinate, substitute that in to the function, which gives us a negative 1. So the vertex here, the point negative 3, negative 1. And once again, the shape of the graph will still be exactly the same. The domain, still negative infinity to positive infinity. The range, however, does change. For this example, the lowest value on the y-axis is negative 1. So the range begins at negative 1 and goes to positive infinity. And example 3, similar function to example 2. The only difference here, now we have a negative in front of the absolute value. F of x is equal to the negative absolute value of x plus 3 minus 1. The vertex is still exactly the same. It's still at the point negative 3, negative 1. But what that negative does in front of the absolute value is it's basically a reflection above the x-axis. In other words, it makes that V open down. So if there's a negative in front of the set of absolute values, that V is basically going to open down. So the domain in this particular case, still negative infinity to positive infinity. The range, here negative 1 is the largest value on the y-axis. So we state the range goes from negative infinity to negative 1.